So in this video, we're going to look at CC13, which is on the groups of the periodic table. And this is a topic that only comes up on paper 2. It doesn't come up on paper 1 at all. So we'll just have a look at the periodic table itself, where you will see that elements are organized into vertical columns called groups and into horizontal rows called periods. In this topic, we're going to be looking at 3 groups in particular. We're going to be looking at the group 1 metals. We're going to be looking at the elements in group 7, and we're going to be looking at the elements in group 0. These elements all have specific names, or these groups have specific names. The group 1 elements are called the alkali metals. The group 7 elements are called the halogens, and the group 0 elements are called the noble gases. And in general, it's important to know that elements are put in groups based on their chemical and physical properties. So by chemical properties, I mean the way that they react, and by physical properties, I mean their physical characteristics, such as what they look like and if they conduct electricity or not. In this video, I'm specifically going to focus on the first group, so the alkali metals, and we're going to see what they have in common in terms of their physical properties, but also what they have in common in terms of how they react. We're going to start by looking at their physical properties. And as we saw from the periodic table, the alkali metals are on the left-hand side. They are indeed metals. So they have properties that are consistent with other metals. Because they are metals, they are malleable. So malleable means that they can be hammered into shape. Because they are metals, they can conduct electricity. So that means they let electricity pass through them. But as well as having those properties that are common to all metals, they have a few unique properties. So you should hopefully know that metals are typically solid at room temperature. That means that metals have high melting and high boiling points. The alkali metals are indeed solid at room temperature, but they do have a much lower melting point than other metals. Because of that, we say they have relatively low melting points. That word relatively is really important here. It's not correct to say that alkali metals have low melting and boiling points. They are still solid at room temperature. But when you compare them to other metals, they do have relatively low melting points. So that word relatively there means compared, and when you're comparing them to other metals, they do have low melting points. Another thing that's different about the alkali metals compared to other metals is that they are soft. So you would consider metals to be hard. The alkali metals are actually quite soft, soft enough that you can cut them with a knife. So they've got certain properties that are consistent with all metals, but then they've got 2 unique properties, relatively low melting points compared to other metals, and they are soft. The other thing we need to look at is their chemical properties. When we're talking about chemical properties, we're looking at how the alkali metals react. If we're looking at their reactions, we need to be looking at their electrons. All group 1 metals have got 1 electron in their outer shell. That's why they're in group 1, because they've got 1 electron in their outer shell. And when metals react, metals always lose electrons. And in the case of the group 1 metals, they will lose 1 electron. When they lose this electron, they will get a full outer shell. So we'll use lithium as an example. Lithium has got 3 electrons. It's got 2 electrons in the first shell and 1 electron in the outer shell. When lithium reacts, it will always lose 1 electron no matter what it reacts with. And when it loses that electron, it ends up with 2 electrons in the first shell. The first shell becomes the outer shell, and the first shell is full. Because electrons are negatively charged, when lithium loses 1 electron, it ends up with a positive charge. If we look at sodium, we'll see the same thing happens. Sodium is also in group 1. It's got 2 electrons in the first shell, 8 in the second, and 1 in the third. So you'll see both group 1 metals have got 1 electron in their outer shell. Because, like lithium, sodium has 1 electron in its outer shell, it will lose 1 electron to get a full outer shell. When it loses that electron, the second shell becomes the outer shell. The second shell has 8 electrons, so the second shell is full. And like lithium, when sodium loses 1 electron, it ends up with a +1 charge. You'll notice as well that when you go from lithium to sodium, you have to add in an extra electron shell That's because lithium is in period 2, so only needs 2 shells, whereas sodium's in period 3 and needs 3 shells. Even though lithium and sodium do react in the same way, sodium finds it easier to lose that electron than lithium does, and you need to know why. This is called the trend in reactivity. So if you're asked for the trend in reactivity of the alkali metals, you will say that they get more reactive as you go down the group. So if we look back at our periodic table, we've got lithium here at the top of the group, then you've got sodium, then you've got potassium, and then down to rubidium. The trend in reactivity is that they get more reactive as you move down the group. That means that sodium's more reactive than lithium, potassium's more reactive than sodium, and rubidium's more reactive than potassium. The most reactive alkali metal will be francium at the bottom, the least reactive will be lithium. As well as knowing that trend, you need to be able to explain it. If we go back to look at how our alkali metals were reacting, you will see that in order to react, they needed to lose 1 electron. The easier it is to lose that electron, the more reactive the element will be. Sodium is more reactive than lithium because it finds it easier to lose that outer shell electron. The reason sodium finds it easier to lose the outer shell electron is because the outer shell electron is further from the nucleus. We know that electrons have a negative charge. In the nucleus, you've got protons which have a positive charge. The negative electrons are attracted to the positive nucleus. In lithium, where you only have 2 shells, the outer electron is quite close to the positive nucleus, which means that there's a strong attraction between the positive nucleus and the negative outer shell electron. In sodium, when you gain an extra electron shell, that negative electron that you're trying to lose is now further from the positive nucleus. This means it's not held as tightly, and it is easier for sodium to lose the electron than for lithium. As you move from sodium, which is in period 3, down to potassium, which is in period 4, you're going to gain another electron shell, which means the electron that potassium is trying to lose is even further from the nucleus. It means the attraction between that electron and the nucleus is weaker, and it makes the electron easier to lose. I've written this out for you here. So they get more reactive as you go down the group. The reason is because you get more electron shells. The atoms are getting bigger and bigger as you move down the group. Because you've got more electron shells, the attraction between that outer shell electron and the nucleus is going to be weaker. And because that attraction is weaker, the electron is easier to lose. Remember, the easier it is to lose the outer shell electron, the more reactive the atom will be. Because there's a greater distance, as the atoms get bigger, it becomes easier to lose that outer shell electron. As well as being able to explain this trend, you need to have examples of chemical reactions that the alkali metals undergo. And the reaction that you need to know is the reaction between the alkali metals and water. I'm going to start with lithium. If I react lithium and water, I'm going to form lithium hydroxide and I'm going to form hydrogen gas. Because I'm forming hydrogen gas, during this reaction, I am going to see bubbles. Okay, hydrogen is a gas, and you will see bubbles. Also during this reaction, you're going to see the lithium move around on the surface of the water. The reason it can move around on the surface of the water is because it's less dense than water, so it doesn't sink. Another thing to note, as well as producing hydrogen, you're also producing lithium hydroxide. Lithium hydroxide is an alkali. That's why they're called the alkali metals, because when you react them with water, you're producing an alkali. And because lithium hydroxide is an alkali, if you took universal indicator and you added it after this reaction, that universal indicator would turn blue because of the presence of the alkali. This is the reaction with lithium and water. If I reacted sodium and water, you're going to see something similar. Instead of forming lithium hydroxide, if I use sodium, I'm forming sodium hydroxide, and again, I'm forming hydrogen gas. Because sodium is more reactive than lithium, you're still going to see bubbles, but you're going to see more bubbles, okay? It'll be more, I'm going to use the word vigorous. Those bubbles, that fizzing that you see, is going to be a lot more vigorous because sodium is more reactive than lithium. Also what you see is because there's quite a lot of heat released in the reaction with sodium and water, that the sodium metal will actually melt and form a sphere. So it will form a little ball of sodium that, like with lithium, will then move across the top of the water. Again, you're producing sodium hydroxide, which is an alkali. So again, if you added universal indicator, it would turn blue. If I use potassium in water, again, I'm going to form a metal hydroxide, this time potassium hydroxide, and again, I'm going to form hydrogen gas. Because potassium is more reactive, I'm going to see very vigorous fizzing. Also, because potassium is the most reactive, you're going to produce so much heat that the potassium will burst into flames and you will see a lilac flame. Again, potassium hydroxide is an alkali, so again, universal indicator will turn blue. You can be asked about the observations you would expect to see of all three of these reactions. You can also be asked to predict what you might see with one of the other alkali metals. So if I go beyond potassium, the next alkali metal is rubidium. So based on what we've seen so far, what might you expect to see if rubidium reacts with water? Well, if you're reacting rubidium and water, you are going to form rubidium hydroxide. And because rubidium is more reactive than lithium and sodium and potassium, the hydrogen gas that you're producing here is going to be very, very vigorous. If the heat released from the reaction with potassium was enough to light the potassium on fire, then you're going to produce even more heat with rubidium and you're going to see a small explosion. So as you're going from lithium to sodium, potassium, down to rubidium, they're getting more and more reactive. So what you're seeing is going to reflect the fact that those reactions are getting more reactive. So I'm just going to look at some typical exam questions that you might get in the alkali metals. So the first one just asks you for the name of the group 1 metals, which is obviously just going to be the alkali metals. So you'll just write down, alkali. The next gives you the observations you would see when you react the different metals with water. Now, you do need to know these observations yourself, and this question they've given it to you, but they could also ask you for the observations. And the first question they ask you about the reaction is they just say, what's the name of the gas that's produced when these metals react with water? And that is, of course, hydrogen gas that's produced. And the next question, they ask you about rubidium. And they tell you it's below potassium in group 1, and they want you to use the information above to predict how long it's going to take for a piece of rubidium to react completely. Okay, so they've given you the time taken for lithium, sodium, and potassium, and you can see as you move down the group and the elements get more reactive, the reaction is quicker and quicker and quicker. Rubidium is below potassium. If potassium is reacting in 5 seconds, you would expect rubidium to react even faster. So when you're asked to predict the time, as long as the number you're writing is less than 5 but more than 0, you're going to be fine. So I'm just going to write 2, but you could write 1, 2, 3 or 4 because that would make it faster than potassium, which is expected because rubidium is more reactive. They also ask you for 2 things that you would expect to see when rubidium is added to water. There's lots of acceptable answers here. You can see what's common to all of the alkali metals is you're always going to see effervescence because you always produce hydrogen gas. So you can write effervescence for rubidium. You can see that they all make an alkaline solution because they are the alkali metals. So you can write makes an alkaline solution for rubidium. You can see that as you move down the group, the elements are getting more reactive. And for sodium and potassium, the metal was melting. You can also write melts for rubidium. You could also say, you see for potassium that the gas evolved catches fire. Well, rubidium is even more reactive than potassium, so you can also say that the gas evolved catches fire, or you could even say that you saw an explosion. Here it says move slowly on the surface of the water, then quickly and then very quickly. Again, for rubidium, you can say it moves very quickly on the surface of the water. So I'm just going to say two of those things. I'm going to say effervescence, and I'm going to say I see rubidium melts. Next, it asks you for a safety precaution. Classic safety precaution, just say you would wear safety goggles, okay, to protect your eyes, and that will get you the mark. Then it asks you for the melting point of rubidium. Again, you're not expected to know this off by heart, but you just expected to be able to fill in the trend. As you move down the periodic table, down group 1, the melting points are getting lower and lower and lower and lower. So the melting point of rubidium should be lower than potassium, but higher than for cesium. So you just need to pick a number that's higher than 29, but lower than 64. I'm going to pick 50, but any number of answers there are going to be acceptable as long as higher than 29, lower than 64. Then it asks you for the name of a group 1 metal that reacts with fluorine more vigorously than sodium. They just need an alkali metal that's more reactive than sodium. As you move down the group, they get more reactive. So you could write potassium, rubidium, cesium, or francium. Any of those will react with fluorine more reactively than sodium will. What hasn't been asked here in these exam questions is just to explain reactivity. That can come up as a 3 or 4 mark question, so please make sure that you can also answer that. And the other really important thing is the properties of the alkali metals. The unique property to the alkali metals is the fact that they are soft and they do have a relatively low melting point when compared to other metals.